So we are going to make a definition called the span of a set of vectors. So if I give you a set of vectors, v1 all the way down to vn, the span of those vectors, and we're going to write it like this, span with the set notation v1, v2, all the way down to vn. The span of these vectors is the set of all possible linear combinations of those vectors. Just to try to illustrate it, here is a set of two vectors, u and v, and I don't really care what they are for now. The span of u and v means every vector of the form alpha u plus beta v. Alpha and beta are some constants. So that means the vector 3u minus 2v is definitely a vector in the span of these because it's a linear combination. The vector 1/2 of u is also a linear combination. Remember that this is 1/2 of u plus 0 v's. That's a linear combination. The vector -v is also a linear combination because this is 0 bunches of u minus 1 bunch of v. So you can take this to its extreme. The vector 0 is also a linear combination of any set because it's what we call the trivial combination. 0 bunches of one and 0 bunches of the other. We are going to talk about the geometric interpretation of span. So if I give you a vector and that vector is non-zero, so if I give you a vector 2, 1, this is a dot or an arrow, however you'd like to think about it. And there's our vector there. If I ask you to describe the span of u, it's any vector that looks like this, t times u. Those vectors could be 0 bunches of u, or 1 bunch of u, or 3.6 bunches of u, or -7 bunches of u, etc., etc., etc. Anytime I take a different multiple of u, it just stretches the vector. Geometrically, the set that contains every multiple of u is a line. Now, I picked a vector in R2, but this is also true for any non-zero vector in R3, R4, or Rn. It will always give you a line. Zero vectors don't count because if you have a zero vector, the only vector you can produce from a zero vector is 0. So this is not true for the zero vector. So here are two separate vectors, u and v. And I would love to know what the span of these two vectors is going to be. Now here I have to be a little bit careful. You should be able to see right here that v is twice u. And so if you want to think about it, any linear combination of these two vectors, so if I were to take alpha u plus beta v, because of this relationship, I'm not taking two different vectors. Really what's happening is I'm just taking different multiples of the same vector. And if I wanted to, I could write things like this: alpha plus 2 beta times u. Alpha is a constant, beta is a constant, both of them are a constant, so I could just collapse this back down to this. And so anytime I were to take multiples of these two vectors added together is just multiples of u. These vectors aren't different enough. And so what this tells you is that, if you wanted to think of it geometrically, I've got one vector here as u, and then I've got another one up there as v. If I were to take any combination of them again, the span of those two vectors is just going to be equal to the span of u or v. It doesn't really matter because they're in some way the same. And this is just going to give me a line again. The number of vectors is kind of important, but it's also, are those vectors different enough? So if I do make my vectors different enough, and I'm being really vague about what different enough is, these vectors u and v are not multiples. The span of these two vectors is any vector that looks like this, alpha u plus beta v. This forms a plane, a sheet of paper. If your vectors are in R2 like they are today, then they basically fill up R2. But if my vectors are in R3 or Rn, the span of these two vectors, u and v, is a plane in R3. In terms of a picture, you'd have a piece of paper that kind of looks like this. The piece of paper would have to go through the 0 vector because 0 is always a linear combination of any vectors. But it would be some sheet of paper on some angle in that space. So the concept of span is important because it gives us geometry. But it's not just about drawing pictures. We are now going to talk about the connection to vectors in R2 or R3 or Rn, and then we're going to see how it connects back to solutions of an equation, and there'll be a wonderful connection.